Another application of derivatives is doing what we call optimization. So optimization means that we're optimizing something, right? We either want to make it as large as possible or as small as possible. And whatever it is depends on the context of the problem. So regardless, a lot of the problems kind of work the same way. So let's just kind of look at some examples of these. So these are typically like word problems where it asks you to find the maximum area of something or the minimum area of something or maximum distance or minimum distance or things like that. So I'll just look at this one. This one says, from this book I'm looking at, it says you have 400 feet of fencing. Okay. And it asks us to make a pen for cattle, right? A rectangular pen for cattle. Okay. So let's just say we want to make a pen. So how would we make this as large as possible? And how do we answer this using derivatives, right? So of course, we first need some kind of equation to work with, right? So that's kind of the first step to a lot of these is making an equation. So let's say that we have the length of the rectangle and the width of the rectangle, right? So just knowing what we know about areas, first of all, if we want to make the maximum area in the pen, we're going to need some kind of equation for area, right? So let's say area is equal to length times width, and we'll just call this A. The only problem with this is that we have two variables, and we only really know how to work with one variable equations. So we want to try to get this into a one variable equation if we can. Luckily, we have some more information, which is that we have 400 feet of fencing. So in other words, the perimeter of this rectangle is going to be 400 feet, right? So that means that 2L plus 2W is equal to 400. Okay. So, and then we could just divide across by 2 to get L plus W equals 200. So what we can do here is we can solve for one of these variables in the second equation, and then we can sub it into this equation, and then that'll give us an equation for area which only uses one variable. Okay, so it doesn't matter which one we replace here. Let's go ahead and replace W, I guess. So W is 200 minus L, so that means A is equal to L times 200 minus L, right? Because that's what W is. And this is equal to 200L minus L squared. Okay. So if we want to find the maximum area, that means we want to find where is the area, where's the derivative of the area equal to 0? Because that's how we can find a local max or a local min, right? So we'll need to find where is the derivative equal to 0, and then we'll verify that it's a maximum. And hopefully with this way this problem is set up, it should be a maximum. So if we find dA, dL, derivative of A with respect to L, we get 200 minus 2L, and we'll set this equal to 0. Again, you can divide by 2. 100 minus L equals 0, so L is equal to 100. Okay. So again, we should verify for A prime that this is indeed a maximum. So if we plug in, say, 0 for L, you get that's positive. And if we plug in, say, 200 for L, then it would be 200 minus 400, so it's negative. Okay, so this is indeed a maximum. In the context of real world problems like this, we do need to pay attention to the domain, right? So like L and W both need to be greater than 0. They don't have like a specific upper bound, just like together they have an upper bound, which is that they added together need to be 200. So that was already kind of built into how we did this, right? By solving for W here. But those are just things to keep in mind. Like if you got that your answer was L equals 0 or L is a negative number, that wouldn't make any sense, right? So when we're working with real world problems, we do need to keep those things in mind. But with 100, we're all good. Okay. And if L is 100, that means that W is 100 as well, because W is 200 minus L. So the largest rectangular pen we can make is actually a square, right? So the actual answer would be something like a square, 100 by 100 foot square. Okay. And you'll get the same thing doing a lot of different problems that are similar to this kind of idea. Okay. Let's do another example, whole different type of problem here. But same general idea. So this one says find the positive integer that minimizes the sum of the number and its reciprocal. Okay. So these are another kind of common optimization problem. They're kind of like little number puzzles. Well, they usually ask you about a positive integer, and they'll ask about the sum or the product of two numbers. Okay. So here we want a positive integer with where the sum of that number and its reciprocal is as small as possible. Okay, so we're only considering positive integers. So the positive integers are, of course, 1, 2, 3, etc. So, I mean, you can kind of just see what this will be just thinking about it, right? If you think about the numbers plus the reciprocal, so 1 plus 1 is 2. 2 plus 1/2 is 2.5. 3 plus 1/3 is, 3.3 repeating, etc. It just keeps getting larger. So 1 should be the answer here. But, if we don't see that, or if we don't, if it's not one we can do like that, how do we set up an equation for this kind of problem? Well, we are asked to find the minimum of the sum and the number and the reciprocal. So let's let the number be n. Okay. That's what we usually use for positive integers, for the natural numbers. And we're going to add it to its reciprocal, which would be 1 over n. And this is what we want to minimize. So we want to think of this as a function, and we want to take its derivative and set it equal to 0. Okay, so no different than the other one. So we have 1 minus 1 over n squared, and we want to set that equal to 0. Okay, so that's 1 equals 1 over n squared, which implies that n squared equals 1. And this implies that n is equal to 1. We don't have to worry about -1 because we're only looking at positive integers. Okay, so we get 1 as our answer, and now we want to make sure that it is indeed a minimum. Okay, so if we plug in, it's a little tricky here. If we plug in, say, like 1/2, when we're just plugging in numbers, we don't need to worry about it being in the domain here. Like it doesn't have to be a positive integer. So if we plug in 1/2, 1/2 squared is 1/4. So 1 minus 4 will be -3. So it's going to be a negative number. And then if we plug in 2, it's going to be 1 minus 1/4, which is 3/4, so a positive number. So this is indeed a minimum using the first derivative test. Okay, so 1 is our answer here. Okay, all right, so let's do at least one more here. Okay, so this one just says we want to find where is the line y equals 5 minus 2x closest to the origin. Okay, so this is another class of these problems where you want to minimize distance in this case, right? And it's going to require the distance formula, which it's probably been a minute since you've really used that. So let's go ahead and look at what the distance formula is. First, let's make a quick sketch of the graph just so we can kind of get a visual. All right, we have a y-intercept of 5, a slope of -2. So it looks something like this. All right, so we're looking for the origin and the point which is closest to it. So something like right there. So we're looking somewhere like 2 or 3 based on the drawing here, but of course we can't trust the drawing. So we want to look at, let's just look at the distance formula real quick, just as a reminder. Okay, so this is x2 minus x1 squared plus y2 minus y1 squared, the square root of all of that. Okay, so we know one of the points is 0, 0. The other point, we can just call, like x comma y. So we're basically looking for the distance between 0, 0 and x, y, which is 5 minus 2x in this case. Okay. So if we think about distance here as a function of x, okay, this is going to look something like x minus 0 squared. So this is just x squared. Don't even need the parentheses. Plus 5 minus 2x squared also would be minus 0. All right. So I'm plugging in just x for one of the x points and 0 for the other x point. And then our y value, which is the value of this line, for one of the y points and 0 for the other y point. Okay. So I get this whole thing. Now I can find the derivative with respect to x here. Okay. So this is, we've got to use the chain rule. So this is going to be 1 over 2 root all this. Okay. Bit of a complicated derivative in here. Times the derivative of this is going to be 2x plus 2 times 5 minus 2x times the derivative of the inner part, which is -2. Okay. So we have this whole thing here. So now we're going to be looking for where is the 0 or where is this undefined. Now we can simplify this a little bit. It's not going to be undefined anywhere because this part's never going to be 0, right? And that should, this just is because, first of all, we're taking a positive number and we're adding it to a positive number, right? Because these are both squared. Positive number plus a positive number is a positive number, so it's not going to be 0 anywhere. The only way you could get 0 is if these are both 0, but that's not possible. This line doesn't go through the point 0, 0. So, and this should make sense too, because this just represents the original distance formula, and we can see very clearly that the distance between these is never 0, right? So we don't even really need to worry about the denominator here. We just really need to worry about where is the numerator equal to 0, because that's going to tell us where is the derivative equal to 0, right? So we have to look for where it's 0 undefined. Here it's never undefined, so we'll look for where is the 0. So we're looking at 2x plus, that's going to be -4 times 5 minus 2x equaling 0. So let's just go ahead and multiply that out real quick. So minus 20 plus 8x equals 0. So this is 10x equals 20. So x equals 2. Okay. So not too surprising here, right? Because that's kind of what it looked like from the graph. We should, of course, verify that it is the maximum. Maybe that's the or I'm sorry, the minimum. We want to minimize the distance, right? There really shouldn't be a maximum here because the line is going from negative infinity to infinity, so there's not going to be a actual maximum. So if we plug in, say, 1, again, the bottom's always going to be positive, so we don't need to worry about that. So just looking really at, we can look at the most simplified part right here. Or really, we can just look at like 10x minus 20. Okay. So if we put in 1 here, that's going to be negative. If we put in 3 here, that's going to be positive. So this is indeed a minimum. Okay. So x equals 2 is the closest point to the origin. And of course, that's not a point. That's the x value for the point. So y minus 5, or y equals 5 minus 2 times 2, which is 4. So it's going to be 1. So 2, 1 is the closest point. And that looks to be about where it is based on our drawing, right? Okay, let's just do one more here. I'm just trying to get like one of every class of problem that you commonly would see in these. And of course, you know, you can kind of apply this to anything, so it's hard to really you know, get every single type you might run into in there. There will be tons of variations and stuff. So let's say for this one, this is one that's about minimizing cost. That's another common type. So let's say we're constructing a box. Okay. The material for the bottom of the box cost $5 per square foot, and it notes that the bottom is square. Okay, so that means that this is really a cube, right? Or not necessarily a cube, I guess, because it implies, you know, all the sides, the heights will all be equal to each other, but they don't necessarily need to be the same as the length and the width. So not necessarily a cube, but so anyway, so the material for the sides is $2 per square foot. We need a box with volume 4 feet cubed, right? 4 cubic feet. Okay. So we want to come up with something that will minimize the cost of this box. Okay, so we want to kind of imagine what this would look like. I don't know if I even want to attempt to draw this. I guess I can give it my best shot here. So we have a square base, right? And then we have some kind of height. And, you know, so it'll look something like this, I guess. So we have the heights, and then these are both x's. Okay. It does say to call the side of the box x, but you can call it whatever you want. So if we call the sides of the box x, and then we have some kind of height, then what kind of information can we get from this? Well, first of all, the volume is length times width times height. So x times x squared times h, which is going to be 4. So we know that. And then we know that the cost is going to be $5 per square foot for the bottom. So the bottom, the area of the bottom is x squared. So it's going to be 5 times the area, right? $5 times what the area is, which is x squared. And then the side of the box is going to cost $2 per square foot. The side of the box, the area of that is x times h, and there's 4 sides of it, right? So there's going to be 4 of them, and then they're costing $2. Okay, and then the area is x times h. So 4 for how many sides there are, 2 for what the cost of it is, xh for what the area is. Now again, we need the cost function to only have one variable. So the easiest to get rid of is h because there's only one of them. And this implies that h is equal to 4 over x squared. So we can go ahead and substitute for h for 4 of x squared. So cost as a function of x is going to be 5x squared plus 8 times x times 4 over x squared. And if you're concerned about 0 being not in the domain, it's not in the domain anyway, right? The side of the box can't be 0. So the cost here is going to be 5x squared plus 8 times 4 is 32. X divided by x squared is just 1x on the bottom. So it's 32 over x. And now we want to take the derivative to get 10x minus 32 over x squared, right? Because 1 over x, the derivative of that is negative 1 over x squared, and then 32 just comes along for the ride. So we'll set that equal to 0. Go ahead and find a common denominator. So in other words, multiply the first term by x squared over x squared. So we'll get 10x cubed minus 32 over x squared equals 0. And again, the denominator can't be 0 because x can't be 0. So we're just looking at where is the numerator equal to 0. So 10x cubed minus 32 equals 0. So we get x cubed equals 32 over 10, which would be 16 over 5. So this is going to imply that x is equal to the cube root of 16 fifths. 16 fifths is, what is that, 3.2? Is that right? So cube root of 3.2. So I'll just leave it as an exact answer here, but you would just go ahead and throw that in your calculator to get an approximate answer. Okay. So it should be like a little bit more than 1. So the minimum cost would be 1 point something here for the x's. And then you would plug that in to h here to get whatever you want the height to be, right? So it's going to be like 4 over cube root of 3.2 squared for the height. Okay, so a messy number, but the math works out all the same. Oh, but of course we should always make sure that it is indeed a min. Okay, so 1 is less than this. So if we put 1 into our equation, and I guess we could do it into this part, but again, this is equivalent and the bottom's always going to be positive. So we really only need to look at the top of it. So 1 put into this would be 10 minus 32, which is negative. And if you want to put in 2 cubed is 8. 80 minus 32 is definitely positive. So again, this will be a minimum.